We are waiting for the participants to join. So I wait for 2 or 3 minutes excess. Then we will start the class. So Bhavani, are you from which background? MSc, BSc, MSc, PhD. Can you hear me? Am I audible? Yeah, I think I will start now. So hope I'm audible to everyone. Can one of you confirm? Yeah, fine. Yeah. We are going to second week of lectures of elementary electrochemistry course. So hope all of you got the opportunity to go through the lectures. Is it? Anyone who didn't go through the videos? Okay, I'll just give a brief outline of the topics covered in this week's lectures. First topic was the estimation of cell EMF. This is something we have already seen in our plus 2 classes, how to measure the EMF of a unknown cell. So I'll simplify the picture a little from the what professor has given in the class. So we have a cell of non-potential E1. Then we have a wire of resistance, high resistance, uh, length AB. So we'll connect the second unknown cell through a galvanometer. It touches X. So the connections are made in such a way that the current from the unknown cell is in opposes the current from the known cell. So let's it be E1. This is EX. So this is directly coming from Ohm's law. So here we have a galvanometer which at a point, a particular point, we are taking that point as X. At that point, it will give a current of 0. In this case, the current is balanced. So we can write V uh, AX divided by VAB is equal to LAX divided by LAB. Here, LAX, sorry, VAB is equal to E1. Similarly, VAX is equal to EX. So we can substitute EX is equal to LAX divided by LAB into E1. So like that, we can calculate the potential of unknown. So this we have done actually. Might have seen on a scale we'll be having a wire of non-resistance, a high resistance wire. which was stick onto a simple measuring scale. From there, we will be connecting a non-cell of some voltage, suppose 2 volt or something. Then below we will be having the unknown cell, something we have a second battery. So using a jockey, we will be moving slowly. At some point, initially it will be moving to towards this direction. Then once we cross the optimum point, that is 0 point, it will go in the opposite direction. So we will find out the length at which it is showing a zero. Then using that, we used to calculate the voltage of unknown cell. So this we have seen in the plus two classes. So one more concept was introduced in the class was the standard Western cell. What is that? So we have two compartments. Here we have liquid mercury. Here we have platinum wire, PT. Here also we have a platinum wire. This is negative. This is positive. Here we have Hg liquid. Then on the other side we have cadmium amalgam. Then above we have Cd SO4 dot 8H2O solid. Then saturated Cd SO4 solution. On this side we have a paste of Hg, paste of Hg with Hg2SO4, like that. So it's this is a standard cell whose EMF is known to be E is equal to 1.01845 volt. So using this we can find out E unknown using the same method, but it is not been used much. I don't know. I haven't seen in the research outcome like this. So before going to the next topic, I would like to, when I was going through the lectures, I thought I'll introduce some more concepts before really going into the week's lecture. So first one is what is an electrochemical cell? So some of the parts like Nernst equation, more derived part is coming in the next week. So before going into that, it's better to know some basic concepts. So what is an electrochemical cell? So electrochemical cell, as you know, there are two types. An electrochemical cell is a device that converts chemical energy into electrical energy or electrical energy to chemical energy. So it consists of two half cells, each of which contains electrode and electrolyte. So one is a reduction half cell, other is the oxidation half cell. The electrodes are part of the cell that carries out oxidation or reduction reaction, and the electrolyte is a substance that conducts ions between the two half cells. So what are the two type of electrochemical cell? One is galvanic cells. Second one is electrolytic cell. So galvanic cell, can you any of you set an example type of batteries? So you can say lithium ion battery, etc. Those batteries are example of galvanic cell. Whereas electrolytic cells, in galvanic cell, what happens? Uh, Chemical energy is utilized to, those are spontaneous reaction. Using chemical energy, electrical energy is generated. Whereas in electrolytic cell, we have to provide electricity to bring about a reaction. So for what is the example? Can anyone tell what is this reaction we have discussed in the last class? What is this? This example, it's a well-known industry. Any of you? I can't hear. It's chloralkali industry. It's a membrane cell. I just give a brief outline of this one last class. So it's a chloralkali industry where anode produces chlorine in the cathode compartment. We have sodium hydroxide and hydrogen evolution. So those kind of even carbon dioxide reduction reaction, all those things comes under electrolytic cells where we have to provide energy to bring the reaction. The reactions are not spontaneous. So we'll say, so I have also seen this year's assignment, so I'm not supposed to discuss that. You can directly write to the faculty or the TA in the announcement. I have also seen, but before the assignment is submitted, I am not allowed to discuss that or what you say, interfere in those things. That's why I have seen question one. So you are expecting a slightly different option, right? Right. So from one region to another region through some circuit. So you can write to that in the forum to the TA. I think Sakshi is from ISAR, Mohali is the TA. So you can write. They will correct it. Yeah, yeah, I understood, but I'm not supposed to discuss that answer, so I'm not going to. So please write to the TA or in the discussion forum. Yeah. So we'll just discuss the what is electrode potential. So when an electrode is dipped in the electrolyte, it have a tendency either to gain electron or lose electron. This is causing them to uh, become positively or negatively charged. Electrode potential appears at the electrode electrolyte interface due to the transfer of charged species across the interface, specific adsorption of the ion at the interface, and specific adsorption or orientation of polar molecule, including those at the solvent. So, what happens when it's called galvanic potential? When an electrode is dipped in the electrolyte, either electrons flow from the electrode to the sub electro at the electrode interface, or it gets electron from the species near to the electrode where the reaction takes place. It's called electrical it's called double layer. So I hope you all know what's double layer. So it's like a capacitor, double layer capacitor. So charge, it's a very huge electric field separated in a very small distance. So it is the reason why we can break while applying the electrical potential, we can break the molecules into some molecule bond into different species. How the reaction takes place. So double layer, there are different theories. One is theory or Helmholtz double layer. Then we have Stern's theory. Then we have something like Goy Chapman theory. So these are not really part of the syllabus. So I urge who are interested can go through the standard textbooks and understand what are these things. These all are different double layer. There are different suggestions or proposals come from different people regarding this double layer. So it's a very useful thing. So you can understand how the reaction takes place at the electrode electrolyte interface. So coming to a portion which has been discussed in the classes, but not implicitly. So how if the potential of a electrode is reported? So the potential of an electrode is reported as standard electrode potential. It's E0. We have seen this E0 value in the lectures. The standard electrode potential is the potential of an electrode at standard condition, which are at a temperature of 25 degrees centigrade, a pressure of 1 atm, and the concentration of 1 mole per liter for the dissolved species. That's how the standard state potential is, electrode potential is reported. So I will ask a question. Can I measure the potential of a single electrode? Can I measure the potential of a single electrode? Can I? No. For that, what we need, how can I? can I measure potential? How can I measure the potential of a electrode? What we need, we have seen something in the lecture. So how can I measure the electrode potential? Something like for a standard Zn 2 plus, mm, or you can write Zn 2 plus bar Zn, which is minus 0.76 versus we will write standard hydrogen electrode. So we cannot measure the potential of a single electrode. We need something called reference electrode. So one kind of reference electrode is called the standard hydrogen electrode. So electrode potential is always reported against a reference electrode. So the standard electrode potential is reported in volts and it is always related to standard hydrogen electrode. Whatever the I'm not going to this next week lecture. I'll be going deeply into what is electrochemical series. So in electrochemical series, we are reporting the potential. It is against the SHE. So at standard condition for SHE, for this reaction, what in SHE, what's the reaction happening? H plus electron gives half H2. So this is the hydrogen elution reaction. So what is the this one electrode? It consists of a platinized platinum electrode covered with platinum black. Why we are using this platinum black? Anyone? These are simple questions I know, but those who are not familiar, they can just go through. Why we use platinum black? Yeah, you can directly unmute and say. No issue. Someone raise the hand. Lavanya. So is it by mistake? So anyone can answer. So high surface area. So then we have a platinum wire, then a hydrogen gas at 1 atm pressure, and it is dipped in a solution of 1 molar hydrochloric acid. So this is the standard hydrogen electrode. But in practical cases, for those who are working in the field of electrochemistry, they know they will be using different type of reference electrode. In the next part, I will be coming to that. The standard hydrogen electrode SHE is defined as a defined to have a potential of 0 volts. So the standard electrode potential of any other electrode is the potential difference between that electrode and SHE. So when you connect SHE with an electrode and measure the voltage in a voltmeter, the voltmeter indicating will be indicating the direct potential of that electrode. That's the advantage of standard hydrogen electrode. So we'll take an example. For example, the standard electrode potential for a reduction of zinc ion to zinc metal is 0.76 volt. This means that zinc electrode has a potential of minus 0.76 volt relative to standard hydrogen electrode. In other words, zinc electrode is 0.76 volt more negative than SHE. These all are different type of representation or how we picturize the cell or electrode potential. So as I just said, so SHE normally in lab scale uses and all, we use some electrodes called AgCl, saturated caramel electrode, etc. These are the schematics for those electrodes. In AgCl, we will be having a silver wire which is partially coated with chloride ions. So which is dipped in a saturated KCl or some different molarity of KCl solution. Similarly, we have HgCl, Hg2Cl2 electrode, which is called standard calomel electrode. So the reaction of standard calomel electrode we will be seeing in the later part today in the today's class. So I'm just showing how does it look like in practical. So these are what we really it look like how a this is HgHgO. This is another type of electrode. It's similar to the Hg2Cl2 electrode. Then another is AgCl. This kind of electrode, this electrode we can easily make in our own lab. So since we have seen the measurement of or estimation of cell EMF, there is one more thing called Ohm's law. What Ohm's law say? If I ampere flows through a solution which offers a resistance of R ohms and potential difference of V volts applied, Ohm's law says that V is equal to I into R. Then consider a conductivity cell which has a two parallel electrodes 1 centimeter apart and each having an area of a centimeter square. Then we know, sorry, this is L. R is proportional to L. Then R is inversely proportional to A. So we have R is equal to rho L by A, where rho is called the resistivity. Resistivity. Then this reciprocal of this resistance is called conductance. Similarly, the reciprocal of resistivity is called conductivity. Molar conductivity, another term we encounter in our problems will be molar conductivity. The conducting power of all the ions furnished by 1 mole of an electrolyte in solution of specified concentration. Lambda m, it is represented by lambda m. Lambda m is equal to K by C. C is the molar concentration of the solution. It is important to note that Ohm's law in electrochemistry only apply to dilute solutions of electrolytes. In concentration solutions, the ion can interact each other, which changes the relationship between current, voltage, and resistance. In electrochemistry, we have three type of currents. First one is, what is that? Faradaic current. Faraday current is something which comes from the uh, reaction involves electron transfer. Second one is ideal. It is coming from the double layer. Then third one is the migration current. It is due to the conductivity of it's something related to the conductivity of solution. So I'm not going deep into that. So in concentration solutions, the current here Faraday current relates to potential in an exponential way, or if you I'm not going into deep because I don't know how many of you have done electrochemical experiments and all. So just for your understanding, there are three type of currents in an electrochemical cell. So what we are interested is the Faraday current. This is the reaction of our interest. So the next part, the really discussed in last week's lecture is the EMF of a cell and free energy change. So how the delta G is related to E? Can anyone? How delta G is related to E? One of you can unmute and speak. Delta G is equal to minus NF into E. Right. So we have another relation called Gibbs-Helmholtz relation, which gives delta G is equal to delta H plus T dou by dou T of delta G at constant pressure. So how many of you know the fundamental relations? So we have some in a quantity called U, which is internal energy. Second one is H, which is enthalpy. Then we have A, which is Helmholtz free energy. Then we have G, which is Gibbs free energy. All of you know what's the fundamental relations defining, or shall I go through a little? I'll just give a brief brush up to your knowledge. So how can you write du? Du is equal to, how can I write? I'll give first one TdS minus PdV. So how the change in enthalpy, internal energy is defined like this. Do you remember, everyone? Yeah. So how H is written in terms of U? H is equal to, how can I write? H is equal to, H is equal to, let's remember, because I wrote this um, Gibbs Helmholtz relation, I will just give a hint. So professor has directly written that. So I will just give a elaborated hint how this equation came. So H is equal to what? One of you. H is equal to U plus PV. So how can I write dH is equal to du plus d of PV, which is equal to, I will substitute TdS minus PdV. Then what will come plus PdV plus VdP. So I'm taking derivative. So this will cancel out. So dH can be written as TdS plus VdP. Then, then what's the next relation? A is equal to U minus Ts. How can I write? dA is equal to du minus dTs. So it can be written as equal to TdS minus P. Hello? Yeah, yeah. Yeah, you can write. Any doubt? Yeah, fine. Yeah, fine. No problem. Minus TdS minus SDT. So TdS cancels out. So we can write dA is equal to minus SDT minus PdV. Similarly, dG is equal to minus SDT plus VdP. Is it clear? How many of you are remembering something called Maxwell relationships? How many of you know Maxwell relationship? Why do we use this Maxwell relationships in thermodynamics? So just to refresh, this won't be coming for your exams, but yeah, someone was answering. Why we use Maxwell relationships? Yeah, that's correct. But I'm not going that um, basics, fundamental, but we use Maxwell relationship for some reasons, right? So no, actually, what happens in when we try to solve something, there will be some unknown quantities. Like we do not know what is the, suppose we do not know what is dP by ds. We cannot directly get the value. So using Maxwell relation, we can replace the dP by dou P by dou S using dt dou T by dou V. That is change in temperature with volume, which is at constant entropy. That is measurable property. So in that kind of cases, we'll use Maxwell relationship. So one example is you Clapeyron equation. Clapeyron equation, then Closures Clay, Clapeyron equation. These equations are application of Maxwell relation. We will use Maxwell relation to derive these equations. You can go back to thermodynamics and see how the Maxwell relations are derived. So I'll just write how. We have one relation called, what is that? Du is equal to TdS minus PdV, right? So I will take the derivative dou u by dou S at V is equal to T. Similarly, dou u by dou V at S is equal to minus P. Again, I am taking second derivative. Dou square u by dou S dou V will be equal to dou T by dou V at S. Similarly, dou square u by dou S dou V. I am taking second derivative for this will be equal to minus of dou P by dou S at what will be V. So what will be the Maxwell relation? So we can write minus dou P by dou S at V is equal to dou T by dou V at S. Is it correct? I'll just cross check method. Dou T by dou V at S. Yeah. So these kind of relations are called Maxwell relations. So similarly, for each of them, dA, dG, everything we can write. So using this equation, here this kind of this one Gibbs Helmholtz equation is simplified. So you can just look into that and understand. So how is we can write this Maxwell relations easily also. Since it's an additional problem solving session, I am just going through it. Otherwise, you don't need to study this portion for exam. So this is not really part of electrochemistry, but it will be useful for you. That's why. So you something called mnemonic diagram you will draw, right? So what is that? VSTP, then AGHU. From this diagram, we can directly write what are the Maxwell relations. So for U, we will write similarly. So U is standing here. So I can write dou T by dou V at S. Since it's pointing to opposite to S, I'll write equal to final exam. You have to consult the NPTEL team. I'm not that aware. Anyway, we will solve number of problems. So whatever assignments given are multiple choice, you have to confirm with the NPTEL team. Whether it will be, it is a exam central exam. So you have to go to the exam center and write the exam. So I'm not aware whether it's a multiple choice questions or it's a descriptive type. You just need to write to NPTEL team. So where we were, so equal to dou P by dou S at V. Since it's pointing towards V, we'll put a minus sign. So you can see dou T by dou V at S equal to minus dou P by dou S at V. So that's what dou P by dou S at V is equal to dou T by dou V at S. So that's how we can easily write the Maxwell relations from this mnemonic diagram. So any of you have doubt how to write? Can one of you try for H how we can write the Maxwell relation? Anyone want to try? You can try and you can tell the answer. For H, how it will be. Do all of you understood how easily we can write from this diagram? Or anyone have doubt? This is not part of electrochemistry, but I'm just brushing it up. Okay, if someone want time, let me know. Otherwise, we'll directly go back to the our course content. This all are part of chemistry. That's why just thermodynamics exactly. So anyone want time, or shall I move on to the portions? So I'm going back to the portions. So you can try to work out it at home. If any doubt in the next class, please ask me. So let it be there. So from where we started it, delta G is equal to delta H plus T dou by dou T of delta G at constant pressure. So now if you link this equation, you'll understand how this relation came. So del G, so we know del G is equal to minus NF into E, which is the Helmholtz relation. So we can substitute minus NFE is equal to delta H plus T into dou by dou T of N minus NF into E. So we'll simplify it. We can write E is equal to minus delta H divided by NF plus T into dou by dou T of E. Dou by dou T of E. Right? At constant pressure. So this relationship is useful for finding out the delta H or E for a non-cell. Is it fine? So one more relation we can write from here is that we have written delta G is equal to delta H minus T delta S. So delta S is equal to what? Dou by dou T of delta G at constant pressure. Minus sign will come because delta H minus TL, but it's plus here. So minus sign will come here. So we can write delta S is equal to minus dou by dou T of minus NFE at constant pressure. So we can write delta S is equal to NF into dou by dou T of E at constant pressure. So you can remember this relationship for problems. So you can expect problem from this relation, which is relates entropy and EMF. Okay. So now, any doubts? So now we will see what's the relationship between free energy change and equilibrium constant. 1 second. Yeah. So here we have the from reaction isotherm we have the relation delta G is equal to minus RT ln Ka plus RT sigma nu ln A. A is the activity. So at standard condition activity can be approximated to 1. So we can write delta G0 is equal to minus RT ln Ka. So this relation we can simplify delta G0, delta G is equal to delta G0 plus RT sigma nu ln A. So we can write E is equal to E0 minus RT by NS sigma nu ln A. Is it okay? So we can also know ln can be changed to log by a factor 2.303. So E0 is equal to 2.303 RT by NF. It's not V, it's nu. That is a stoichiometric coefficient. So you can write also sigma ln A raised to nu. It's a stoichiometric coefficient. That is, suppose we have a relation, okay, A plus B divisibly giving C plus D. So this A, B, C are called stoichiometric coefficients. So nu represents stoichiometric coefficient. So for products it's positive, for reactants it's negative. So where we were? So we can write is where I stopped. Oh, sorry, log k. So from we started here. So we, yeah, 1 second. I miss something. Friends, no, yeah. So we have omitted one step, so that's okay. So E0 is equal to at standard at 298 Kelvin, 298 Kelvin, and standard state you can write E0 is equal to 0.0591 by N log Ka. So this is the simplified one. So standard state, what's the value of R? 8.314 joules per mole Kelvin. T is equal to 298 Kelvin. And what is that? F is equal to 96485 coulomb per mole. So like that, this we will substitute these values and we will get a simplified. So when you do electrochemical experiments, if the system is perfectly reversible, you will say the peak to peak separation will be 60 millivolt. So this is the value coming, that 59 millivolt, so we will say roughly it's 60 millivolt. Like that, this is the value coming for that. So for a single electron process, it will be 59. So what's the next one? So we'll take an example for Daniel's cell. For Daniel's cell, we have zinc plus Cu2 plus will be giving Zn2 plus Cu, right? So how will you write the equilibrium constant? K in terms of activity, you can write activity of Zn2 plus into activity of Cu divided by activity of Cu2 plus into activity of Zn. So for pure elements, we can take it as 1. So which is equal to activity of Zn2 plus divided by activity of Cu2 plus. What is the standard potential for a Daniel cell? E0 equal to what? Daniel cell. What is E0 value for the Daniel cell? It is 1.1 volt. How it's coming? For cathode, Cu2 plus bar Cu, we have 0.34 volt versus RHE or sorry versus SHE. When you write a potential, always try to write with the reference. Then for Zn2 plus bar Zn, you can write minus 0.76 volt versus SHE. So how can you, yeah, so how can you write which is anode and which is cathode? So that's the last portion sir was discussing in the class. So that portion is not fully covered. So we, yeah. So when we have a electrochemical series which is more negative, we will consider as anode, which is less negative, we will consider it as cathode. That is higher value in terms of absolute, not absolute value, real value system. If you take real numbers, which is higher, we will take it as cathode, which is lower, we will take it as anode. So in this case, copper will be the cathode and zinc will be the anode. So we can write 0.34 minus 0.76 to 1.1 volt. So how you can use E0 is equal to 1.1 volt. So using that, you can write Ka is equal to, it's approximately, I didn't calculate it. Ka is approximately in the range of 10 raised to 37. That is activity of Zn2 plus by activity of Cu2 plus is in the range of 10 raised to 37. So like that, you can calculate the equilibrium uh, constant using this relationship. So I'll go to the final part what I was discussing in this week's lecture is type of electrodes. Yeah. What are the four types of electrodes? First one, can anyone? What is the first type of electrode? Here I'll discuss what sir was giving us homework also. So I'll try to discuss that part also. So what is the first type of electrode? metal, metal ion electrode. Can one of you unmute and say example? Yes, refresh your memory. What? Yeah. No, no, this is a single electrode we are saying. You are telling about a cell, full cell. So, yeah, you can write zinc 2 plus. It can be what's the reaction? Sudden gives, reversibly gives Sudden 2 plus 2 electron. Similarly, you can write Ag bar Ag plus. What's the reaction? Ag gives Ag plus electron. So similarly, copper also you can write copper Cu2 plus. So what is that? Cu reversibly giving Cu2 plus 2 electron. So these are first type of metal ion electrodes. Then what was the second type of electrodes? Gas electrodes. What is an example of gas electrode? This is a famous electrode, right? Standard hydrogen electrode. Reference electrode. What is the reaction taking place in standard hydrogen electrode? H plus electron is reversibly giving half H2, or you can write 2H plus 2 electron give H2. There is nothing like half H2 exists. So it's better in the write in the balance form, or you can write like this also. So the third type of electrodes will come metal sparingly soluble salt electrode. What's the example? Ag, AgCl. This is a comma KCl aqueous. This is a non-reference electrode we all use in our lab. So what is the reaction taking place? So first Ag solid will give Ag plus electron. Then this Ag plus Cl minus gives AgCl. So what is the overall reaction? Ag plus sorry. What is the overall reaction? Ag plus Cl minus Ag cancels out. Ag plus Cl minus gives AgCl plus electron. This is the overall reaction for AgCl. So next one, you had to try yourself. So what was that? Hg Hg2 Cl2 comma KCl. What is this electrode called? What is this type of electrode called? I already, yeah, it's called standard calomel electrode. Yeah. What is the reaction? Can anyone unmute and say? Yeah. 2Hg reversibly gives Hg2 2 plus 2 electron. Then in the next step, this Hg2 2 plus 2 Cl minus reversibly gives Hg2 Cl2. So what will be the overall reaction? 2Hg plus 2Cl minus reversibly gives Hg2Cl2 plus 2 electron. Fine. Sorry, saturated caramel electrode. That's correct. Saturated caramel electrode. That's correct. Sorry. It's saturated with KCl. Yeah. Then what was the third example? PB bar PB PbSO4 comma K2SO4 aqueous. So what will be the reaction? Pb gives Pb2 plus 2 electron, where Pb2 plus again reacts with SO4 2 minus gives PbSO4. Similarly, the overall reaction will be Pb plus SO4 2 minus gives PbSO4 plus 2 electron. Fine. Then fourth type of oxidation electrode is uh, oxidation, oxidation, reduction electrode. So in the first case, we have seen a metal and metal oxide is in contact. In this case, we don't have a pure metal. Example is Fe bar, Fe2 plus bar, Fe3 plus. So ferroferric. This is a standard system we use for so many examples in our lab. And second one is Sn2 plus bar, Sn4 plus. So how can we write Fe2 plus gives Fe3 plus electron, or Sn2 plus gives Sn4 plus 2 electron. Fine. So this is the overall content. I have added little more contents so that you all will refresh your memory. You might, all of you might be knowing all this content, but so I just try to refresh some of the concepts and basics of electrochemistry and electrochemical cells. Then we have just seen what all things uh, were the content for this week's classes. So these classes, actually the completion will be coming in the next week through the Nernst equation. I think some of you have already seen third week videos also. So now let's solve some problems. So can one of you read the question? Please don't mind this kind of joule per mole Kelvin. So when I'm converting it to my iPad, it's losing its compactability. So please don't mind that. Can one of you read this question? Or I will read. Calculate the entropy change for the following electrochemical cell. PT solid bar H2 gas, formic acid CH3COH, HCl, salt bridge KCl aqueous bar Hg2Cl2 bar Hg. Given EMF of the cell is 0.054 at 298 Kelvin. Temperature coefficient of the cell is 5.4 × 10⁻⁻⁴ volt per Kelvin. So how can we solve, calculate the entropy change? We are asked to find delta S. I'll give 2 minutes for solving. So once someone finish the question, please put a message. Done. It's a straightforward question. Anyone? Are you able to figure out the equation? Anyone finish? Or shall I solve? Anyone? So shall I start solving? Yeah, I think I will solve it. So first, whenever get a problem like this, we will write the half cell reactions. So what is the anodic reaction? At anode, we can write H2 gives 2H plus 2 electron. So at cathode, we have Hg2Cl2 plus 2 electron gives, so now we need to put this reversible sign, gives 2Hg plus 2 chlorine Cl minus. So then we have 2H plus 2Cl minus gives HCl. So what will be the overall reaction? Overall, it will be H2 plus Hg2Cl2 gives 2Hg plus 2HCl. So you can see here it's plus 2, it goes to 0 here. So 2 electrons are involved. What is the relationship for delta S? What is delta S? One of you. Delta S is equal to NF into dou by dou T of E, right? At constant pressure. So you have to remember this equation. So that's why when I was refreshing, I told you have to remember this equation for solving. Here you can see d by dt has a unit of volt per Kelvin. So that value is given. So you can directly substitute, which is it is 2 electron process. So 2 in delta S is equal to 2 into 96485 into 5.4 into 10 raised to minus 4. So the answer will be coming 104.2 joule per Kelvin. So unit also, usually entropy we will write delta S, and its unit is joule per mole Kelvin. So here we have taken moles also, so we will say joule per Kelvin. Is it clear? Is it clear? Which one? The negative sign. You're telling delta S. Please show the slide again. Yeah, it's short. No, delta S will be positive because delta S is, we are, uh, 1 second, I'll come back to the slide. So delta S will be coming positive. Where is it? Yeah, delta S is positive because you see delta S is the minus of dou by dot of delta G. Delta G is minus NF into E. So that minus sign will come out. So finally delta S will be positive. Delta S will be NF into dou by dot of E at constant pressure. Yeah, I'll come back to that slide. Yeah. Hope it's clear. So that negative cancel out. That's why it's coming positive. Is it done? Can I change the page? Temperature, why you need temperature? It's dou E, you see the temperature coefficient, that is dou E by dou T at P. That value is entirely given as 5.4 into 10 raised to minus 4. It is 10 raised to minus 4. 10 raised to minus 4. So when I'm converting, it's coming like that. So that coefficient is given. You just need to directly substitute that. So remember this word also, temperature coefficient, which is nothing but dou E by dou T at constant pressure. Unit also you can cross check. It's volt per Kelvin. Volt per Kelvin. Yeah, is it fine? So the EMF of the cell is also given. E is equal to 0.054 volt. So can I ask, can you calculate delta G? Can you try to calculate delta G? What will be delta G? Delta G is equal to minus NFE. Please calculate. NFE, E is given. So it will be minus 2 into 96485 into 0.054 equal to what's the value? Minus 10.42 kilojoule. Yes, the answer is minus 10.42 kilojoules. So it's direct. I just added the question. Is it fine? Question? If everyone done, we will move to the next question. Yeah, that's fine. You can write. The last class also I have written in many ways. So F is equal, the F value we can write 9648. Yeah. Answer, you see, if it is a multiple choice question, so you'll be getting answers like minus 9.2, minus 10.4, minus 11.6. So if you change, how much it will change? It may go up to minus 10.6 maybe. So the answer will be well distinguished. No problem. Actually, this is the exact value. So how we are getting it? We'll multiply number of electrons into charge of electrons. Our gathered number into charge of electrons. So the value is 96485. So we will, for simplicity of calculation, we will take it 96500. The actual value is 96485. So it's better to follow that value. Yeah, someone calculated and showed it's very close. So even though it's a multiple choice question, you will get the answer. So you can use 96. The answer is simple answer is you can use 96500 as well. 96485 doesn't matter. The answer will slightly vary. The purpose of this problem is understand the concept. So if it changes a little, it's okay. So I urge you to use this 96485 itself. So that's the correct number. Fine. But you know, right, how the value came 1.6022 into 10 raised to minus 19 coulomb into 6.022 into 10 raised to 23, 22. So how much? 22 or 23? 23. So this value will 96485 coulomb. That's how it came. So for simplicity only, we are taking it 96500. How? You just took the calculator and multiply 2 into 96485 into 0.054. No, that is kilojoule. It's coming joule 10,420 joules, which is equal to 10.42 kilojoule. So I wrote the unit as kilojoule. Got it? Yeah, fine. So shall we move to next question? Yeah. There's a direct question. One should have. What is the potential of standard hydrogen electrode at standard state? What is the potential? 0 volt. So just a direct question. So we'll go to next question. For a cell, if delta G of the cell reaction Ag plus electron gives Ag plus Cl minus is minus 51.5 kilojoule, the standard EMF of the cell is. Direct question. So all of you calculate and tell me the answer. Yeah, all of you. I'll directly solve this problem. So what is the formula? Delta G0 at standard state, delta G0 equal to minus NF into E0. So we can write how many electrons are involved? One electron. 1 into 96485 into E0. So which is equal to minus 51.50 into 10 raised to 3 joules. So I minus NFE, minus positive. So E0 will be equal to 0.53 volt. Clear? Shall we move on to next question? Everyone solved? Yeah. Moving on to next question. For an electrochemical cell reaction involving a two electron change, the standard EMF of the cell is found to be 0.591 volt at 25 degrees centigrade. 25 degrees centigrade. The equilibrium constant for the reaction at 25 degrees centigrade is, this is 25 degrees centigrade. Can you calculate? Don't comment the answer. So if you are finished, please put done. It's also a straightforward question. I'll give a hint. Delta G is equal to minus RT ln K. Standard EMF is given. So you have to convert and do. Yeah, try to solve this. Once the answer is done, please comment done. Once one more person says done, I'll solve the problem. It's a straightforward. What's the difficulty? If anyone faces difficulty also, please unmute and ask. We'll solve it. So what's the answer coming? What's the answer? Yes, shall I solve it? So it's straightforward. So delta G is equal to NFE. So you can write minus NFE minus NF E0. Oh, you have missed some part. Order of magnitude. There is a huge order of magnitude difference. NF E0, which is equal to minus RT ln Ka. So how can you write ln Ka is equal to NF by RT into E0. So E0 value is given. So we can write 2 electron process 2 into 96485 divided by 8.314 into its standard condition 298 Kelvin into 0.591. The answer will be Ka is equal to, you have to take 10 raised to that answer. It's actually ln is coming here, so you have to take e raised to answer. So it's equal to 9.8 into 10 raised to 90. I don't have calculator. Figure it out. Why? How did you get Dilkush? I Can you unmute and say? Right. Let me also calculate one. So the answer comes 9.8 into 10 raised to 90. So 2 into 96485 into 0.91 divided by 8.314 divided by 298. Then because I don't have scientific calculator now. So 2 into 96485 into 0.591 divided by 8.314 divided by 298. So the ln Ka value is 46.03. ln Ka is equal to 46.03. So you have to take e power, that value, e power, what is power? Yeah, e raised to 46.03 is 9.78 into 10 raised to 90. That's the answer. Is it clear for everyone? Dilkush, you have posted some different answer. Since everyone was getting different answer, I just recalculated it. So answer is coming 9.7. Yeah. Just try to calculate once again. So it's just substitution. Don't forget to take 2 electron. It's a 2 electron process. So you have to take N is equal to 2. Temperature you should convert it to Kelvin. One second, one second. Can you repeat? Yeah, why you want to use that? Here also it's direct, right? Yeah, RT by, you can use that, no problem. The same one, you just substituted that, right? RT by NF. How it comes? RT 8.314 into 298 divided by 96485. One second, there is one problem. It's log. In that case, you have to take 10 raised to. You see that one, we have did something right. So 2.303 RT by NF log Ka. It's log. It's log to the base 10, where in this formula you are using ln, which is natural logarithm. So you have to consider that answer will come the same. Clear? We can use that formula, no problem. Is it done? In that case, we can move on to the next problem. Shall we? Or anyone have doubt? Just stick to the basic calculations. So if you want to take anti-log, if it is ln, it will be e raised to. If it is log, it will be 10 raised to. That's a basic thing you have to remember. Shall we move to next problem? Anyone have any doubt? If there is no doubt, we'll move on to the next question, fifth question. Calculate the equilibrium constant Kc for the reaction Cu plus 2Ag plus reversibly giving Cu2 plus 2Ag. The standard EMF of this galvanic cell is 0.46 volt. Standard EMF is given. Then the reaction is given. So how will you calculate? So we'll try to solve it in the way Bhavani said. Like we'll take that simplified form and solve. Try to solve this problem. Reactions. Slowly. Is it done? Or anyone have doubt? Shall I solve this problem? Now, Kc is based on concentration. Ka is based on activity. So I will give one more hint. Kc, in this case, you can take the system is in equilibrium. In equilibrium, what will happen? What will happen to E cell? What will be the value of E cell at equilibrium? So if you can get that idea, you can directly solve the problem. So I'll solve this problem. So at equilibrium, E cell equal to 0. So what is the formula? E cell is equal to E0 cell minus 0.0591 by n log Kc. Note that log Kc. So we can write 0. What is the value given? I forgot. 0.46. 0.46 is equal to 0.0591 divided by 2 log Kc. Can you find what is Kc? It is log. You have to take 10 raised to 10 to the power. What is the value of Kc? Yeah, you can directly ask if any questions. So at equilibrium, the forward and reverse reactions are at the same rate proceeding, right? So if you take a cell also or your reaction system, if you measure the OCP, it will be starting from 0. It will be against standard hydrogen electrode, not like AgAgCl. So at equilibrium, hello, Bhavani, you are asking something. Yeah, yeah. So here we are asked to find the equilibrium constant. So since Kc they asked, we'll take the system is at equilibrium. At equilibrium, the system E cell is 0. So how it comes, I will show you the derivation in the next class. So don't worry. So at equilibrium, the cell potential will be 0. So using that, you can substitute the value E cell is equal to E0 cell minus 0.059 by L log Kc. So from that you can get Kc. So Nernst equation is coming. In that case, I'll show you clearly why at equilibrium, what happens. It's a direct substitution only problem. So as we have already seen, we have actually the equilibrium, whatever coming in the delta G expression and all, it is log activity. So when we simplify it to standard state and all equilibrium state, it's we can replace it by concentration. So most cases in Nernst equation and all, we will be seeing concentration terms, but actually it's activity. So what's the simplification is coming? How at equilibrium what happens? You will see in the next class. So don't worry about it. So now please take it as at equilibrium easily 0. What's the answer coming? Yeah, log can be written as 10 raised to. Yes, Kc you have to find. No, no, no. You have to multiply 0.46 into 2 divided by 0.00591. That value you have to take 10 raised to. Yeah, no problem. 0.46 into 2 divided by 0.0591 is equal to log Kc. So what's the value coming? Let me take the calculator once. Oh, 0.46 into 2 divided by 0.0591. It's coming 15.56. So, right, 10 power 15.56. So the answer, so this value is coming 15.56. We'll take 10 raised to 15.56. Answer will be equal to 3.69 into 10 power, what is that, 15. Is it clear? Yeah, it should come the same value. So I have to check it. So other formula it's nothing actually. Instead of this ln, you have to write RT by NF. What is that other formula? You can write RT by NF ln K. Value will come the same. There won't be any difference because one is e raised to. For compensating that, we are taking 2.0303. 3.69 is the magnitude. 3.69 into 10 raised to 15. Okay, I'll write it properly. 3.69 into 10 raised to 15. It's a equilibrium constant. It doesn't have a limit. Is it clear? So the delta G relations will come into picture. Delta G is equal to 0 at equilibrium. So okay, okay. Okay, we were discussing. So don't worry, this video will be shared by the NPTEL team soon. So you can refer to those the missed questions after that. No worries. If any doubt, you can ask in the next class also. Shall we move to next question? This question was which is ambiguous. So we'll discuss it little in the next class, starting or ending. So like last class, someone asked one doubt. I have in the backup slides. So don't worry. So we'll solve we'll solve two simple problems and stop for today. What is the cell potential of a electrochemical cell? Pb2 plus cadmium gives Pb plus Cd2 plus. So I'll write it down. Pb2 plus Cd gives Pb plus Cd2 plus. Given that E0 cell is equal to 0.78 volt at 25 degrees Celsius and cadmium 2 plus concentration is 0.01 and Pb2 plus concentration is 0.1. So Nernst equation, please try to solve it fast. So we have E0 cell. Using that, you have to find out E cell. So I'll just write the equation. E cell is equal to E0 cell minus 0.0591 divided by n log Kc. So it can be written as equal to 0.378. That's the value, right? Given minus 0.0591. How many electrons involved? It's 2 plus 2, 0. That means 2 electrons involved. So by 2 log of product concentration, that is CD2 plus concentration divided by PB2 plus concentration. So what will be the value coming? Can one of you finish? Is it assignment question for this time? I don't know. But the 23PG114, that user, please check the signs. So you have just missed, I think, something you missed. I think maybe the n value. There will be differences. There may be similarity to the assignment question, but there will be differences from them. So the answer is coming 0.4086 volt. So 76 volts someone got, I got 86. So I might have also taken some values different. So it's coming around 0.408 volt. Is it clear? This reaction is two electron process. So Pb 2 plus 2. What? It's, you see the overall cell reaction we have written, right? So what is in the product side, we will take the numerator. What is in the reactant side, we'll take as numerator, denominator. Then for pure ones, we have taken it as unity. Like that it can. Once you finish writing, let me know. We'll go to the next problem and finish today's class. Next one, we'll see a simple problem. What? 0 point? No, 0 point. How you are getting that answer? Can you explain? Hmm. Hmm. Wait a minute. It's 10. It's 10 raised to minus 1. Okay. Let me calculate it. Answer will be 0.408. Others also got the answer. I'll just clearly tell you. Log, log. What's the value of log 10? Hmm. It's straightforward, right? So log, it's a log 10 raised to minus 1. How can you write that? You can take the minus outside. So you can write 0.378 plus 0.0591 divided by 2 log 10. Log 10 is 1. So the answer will be like 0.0591 divided by 2. But the sign will change to plus 0.378 plus 0.0591 divided by 2. So it will be coming 0.4086. You might have done some calculation mistakes. Yes, correct only. 0.378 minus 0.0591 divided by 2 log of what is cadmium concentration? 0.01. 0.01 divided by 0.1. So how can you write this? I'll go to next page. It is 0.378 equal to minus 0.0591 divided by 2 log of 10 raised to minus 1. This I will take out. So it can be written as 0.378 plus 0.0591 divided by 2 log 10. Log 10 is 1. So it will be like 0.378 plus this value. So what's that value coming? Am I used it wrongly? Okay, okay. You might have used 0.591 instead of 0.0591. Yeah, Arjun is right actually. If you use 0.591, the answer will be coming 0.6735. So there is 0.0591. It is actually 60 millivolt, the value. Is it clear? No? Are you getting the correct answer? So you should just need to substitute the values. You will get the correct answer. Yeah, yeah. Shall we move to next question? Yeah. Last question. The cell potential for the cell is, what's the answer? So this is a cell reaction Al bar Al 3 plus 0.01 molar Fe 2 plus 0.01 molar same molarity bar Fe. Sorry. So minus 1.706 volt. How will you calculate this? Ask cell voltage. Notice these concentrations are same. So E cell is equal to E0 cell minus R 0.0591 divided by N. You can use it. Why it's happening? That's why I was. It's simple because the concentrations are same. So this term will be log 1. Log 1 is 0. So this entire term will goes out. So E cell is equal to E cathode minus E anode. What will happen in that case? Which will be cathode? Iron will be the cathode. Minus minus 1.706. What will be the answer? Yeah, fine. How 1.6651 came? Bhavani, what does that value came? So it's just E cathode minus E anode. Since the concentrations are same, the log term will can be 0. Yeah, yeah. Just recalculate it. No, this is actually last year assignment questions. So exams also you can expect this kind of questions. If the concentration is different, the log term will be also coming into picture. So we will be getting a different E set. Since here concentration is same, so it's numerically I just shown. So if the since the concentration is same, it came log 1, log 1 is 0. That's it. There is not much to think about it. Yeah, is it done? So last class someone was asking why these eccentric wheels were shown. So I was also not knowing that answer. So this is given to do something with the bottom layer of mercury. The bottom layer of mercury can be put in motion with the help of eccentric wheel. So here it will just to give a motion to the liquid mercury filled at the bottom. So top, these three portions won't be mixing, but at the bottom, they'll just give a motion to the liquid mercury. For that, this eccentric wheel is given. So it's a old process. So I just went through the internet and I got the answer. So since someone asked, I just put the answer. So it's not that important to the chemistry perspective, but still it's good to know. So that was a good question. So I also went back and checked what's the answer. So this was someone asked last time why the eccentric wheel was given. So the answer is just to put the liquid mercury at the bottom in motion, just to give a little movement for that liquid mercury. Yeah. Okay. So we are done for the day. So hope these sessions are useful. So don't worry about the this year assignment question. So you try to solve it. If you are having any doubt, if the you're feeling the options are wrong, just directly write to the what do you say the forum or the NPTEL forum, so I cannot interfere with those questions. So we'll try to solve the questions after the assignments are done. So 7th is the last date for first and second assignment, right? After that, we will try to solve those problems. Okay, okay. That question I am also little doubtful. I will get back to that. I understood. Its answer. What is the electrode used? So for chlorine evolution, ruthenium-based electrodes are mostly used. So for hydrogen evolution reaction, platinum, platinized carbon, those kind of electrodes are very good. So if E0 cell is given, we can directly calculate what is the equilibrium constant, all those things. But more details need to be given for solving that problem. We have to take a lot of assumptions and solve that problem. So if it is at the standard state, I think you can directly answer the question. So type of electrodes for chlorine evolution reaction, industrial scale also they are using mixed metal oxide. It is a mixture of ruthenium, titanium, etc. Those kind of electrodes are used for chlorine evolution reaction. Whereas hydrogen evolution, platinized carbon, those kind of electrodes are used for it. Platinum have very good. Platinum is a very good catalyst for hydrogen evolution reaction. That's the right now. That's the answer I have. Then you can take some assumption and try to solve that. I'll also try to solve that question. I understood the question, so I'll also try to solve that question for the next class. Is there any other doubts? If not, we'll wind up this class here. So next week we'll be seeing more of Nernst equation, liquid junction potential, then concepts like what is concentration cell, all those things we'll be seeing the next class. It's what? Sixth question. Your seventh question, I think this one. Yeah, seventh question. This one. No, this is 1.297 answer. This is direct substitution. Minus 0.409 minus. It will be plus. It's like Daniel cell calculation. Will 0.34 minus 0.76. So it will be 0.34 plus 0.76. It will be 1.1 volt. Yeah, yeah. Here because the concentrations are same, so this term is cancelling out. Log 1 is 0. Like that it's coming. That's why I just wrote there. The term will be 0. Yeah. If there is no more questions, we'll just wind up this session. So thank you everyone. Thanks for joining. So we'll try to make these sessions more interactive. So if you feel any doubt, you can ask. If I know the answers, I'll be directly answering, or in the next class, I'll try to answer those questions. Yeah, see you everyone. Bye.